So I'm Nicholas, a PhD student as part of the Sino-Danish Center, which Birte presented this morning. My research topic is essentially building a digital twin framework to evaluate industrial consumers' demand response participation, so participation in energy markets. And this is done in a context of comparing the Danish and the Chinese energy markets. So just to give a bit of context, why is demand response needed in both of these countries? Well, if you look in the graph on the right, you see that Denmark is leading in terms of, or at the forefront of integration of variable renewable energies. But China is actually also doing quite well if you split it up into its different regions, and especially the regions in the northwest have a high share of wind. And so they have a strong need for flexibility, as this picture from the IEA explains. And this has posed a few challenges for both of these countries. In some of the regions in China, there's up to 40% wind curtailment in some years. And Denmark as well has some difficulties with, for example, shows volumes in the down regulation market, where essentially you pay wind turbines in Denmark to be shut down at certain hours because there's no one to consume that power. And so that naturally kind of leads to a demand for this more flexible consumption, so shift consumption based on either price signals, requests, or own incentive. And that's generally referred to as demand response. Now, the question is, who should we apply this demand response to? So this research focuses on industrial consumers. And of course, they have a few advantages. The fact that they have large loads means that there's no aggregator needed, which means they're more in control of where they bid their demand into the market. The fact they already have sensors and actuators in place for the processes means that the investment cost in demand response is usually lower. And the fact that they have a more profit-driven mindset means that they have a more rational behavior towards price savings, and that makes it a bit more easy to model. Of course, these disadvantages at the moment are kind of offset by a few barriers. I've underlined in red the ones that depend kind of on the industrial consumer itself. So there's deep domain knowledge required usually, and that's something that's been clearly shown in Daniel's presentation with interaction between processes, which needs a high level of simulation. So which means that there's a certain uncertainty in terms of the impact of demand response. There's an unwelcome operational risk in that case. And this risk is not necessarily offset by the financial returns of participating in the market. So that in general makes industrial consumers reluctant to participate. And then of course there's external factors such as price dynamics and market regulations, which can be barriers, but the industrial consumers can't do much about that. So what this project is trying to do is to basically develop a digital twin to increase the market participation confidence, to produce results in the sense that this sense of risk and uncertainty is reduced, and then the advantages kind of overweigh the barriers. This is then applied. Why do we use a digital twin specifically, or why this is a specific tool? And to understand that, I think it's important to have three assumptions in mind. The fact that electricity cost is not the main driver of production schedule. So there's the logistical schedule to take into account, the production schedule. And so that makes it kind of a multi-objective problem. And that means you need to explore multiple scenarios. So it calls for a scenario-based approach. That's number one. Number two is that industrial consumers, as I mentioned, prefer to keep control of their schedule. So that means you want to provide a descriptive approach of what happens if I do this, instead of a more, I would say, prescriptive approach. That would be kind of the resultant of an optimization program where you have one end output and this is what you shall follow. So this is more a preference for simulation. This is number two. And number three is that market participation is simulated from the industrial consumer's point of view. That means we're not simulating the system as a whole. So we're not simulating market prices, etc. So instead we're importing external data as our market prices we use to make our decisions. Essentially, if you combine the need for scenarios in a simulation with large-scale data, that basically are the components that call for the need of a digital twin. Now, this is then applied, as I mentioned, in two different contexts, China and Denmark. Denmark is considered a typical deregulated market with essentially different actors taking on different responsibilities. And that's shown by the range of different market options you have in a deregulated market context. It could be day ahead, or actually, as we've seen in the presentation, there's a more short-term markets, etc. And so the industrial consumer has a choice essentially of markets in which you can participate in. On the other hand, in the Chinese more centralized system, you have a more, at the moment at least, a more like top-down approach where prices are given to the consumer. So they're less involved into the actual price, into the actual volumes traded in the markets. And that implies that the industrial consumer will have a different role in these different contexts. So in this context, the aim is to develop a digital twin framework for energy markets. And I've underlined framework because essentially it has to be generalizable enough to be applied in the Danish context as well as the Chinese context, which, as we've seen, are very different. And the aim is then to facilitate industrial consumers' participation in electricity markets with their energy flexibility. And that's done kind of by trying to meet three different objectives. The first one is what I would call a pre-simulation stage, where on one side you try to characterize the types of flexibilities of different processes, and on the other, the types of, well, the market options you have in a specific market context. And then you try to have this like process to market matching. So which process would actually suit most which market option. And then in the second step, this is the actual simulation itself with the model framework being implemented. And then the third step is, maybe you could call it a meta simulation. So essentially by repeating your simulation enough times, you can get a general framework out of it. You can draw some general conclusions on how demand response can best be integrated into electricity markets. So that's kind of what this structure would look like with the three different objectives being shown as three different parts here. And I really want to stress the iterative approach here. So the more industrial processes you go through, the more generalizable this approach becomes. And the more markets you analyze, again, the more generalized your problem becomes. So and this is much more of a high level approach than maybe some of the topics we've seen so far. But I'll dive into the different parts now one by one. So in part one, as I said, it's more of a process to market mapping. So in terms of the process, you need to be able to describe it in terms of a very few parameters which describe the process. So from the operational requirements side, there's questions of how much flexibility do I have? What share does it represent of my overall consumption? For how long can I shift it? How often and how fast? And then there's also more, let's say, subjective parameters, which are the consumer preferences. What are their return on investment expectations? What are their risk willingness? And these will all influence essentially the flexibility they're willing to bid into the market. And on the market side, you have the regulations, which will determine whether a market player can participate in the market or not. And you have the price signals, which determine whether it is actually attractive to participate or not. So how variable are the prices? How often is the market actually activated? What is the liquidity of the market? So how many people actually participate in that market? And so essentially when you match, once you have these different parameters, you can match what process would fit best with each type of market. And then in the simulation stage, we're using also agent-based modeling, which has been presented in a few presentations before. So agent-based modeling is essentially like dynamic interactions between rule-based agents. So the advantage is you can model complex systems by breaking down in the logic into different subcomponents and then see how they interact on a more time-based simulation. And that has a few advantages in a market context. One of them being modularity. As we've seen, different markets need to have different structures. So, but in the end, you still have the same basic role functions. You still have the consumer, the generator, etc. The question is, how do they interact? They will interact differently in different markets. So these basic roles you can then, in a modular way, as building blocks, combine in different ways. And then a second advantage of agent-based modeling is, as I said, this individual logic you assign to each agent allows to give behavioral factors to your consumer. So for example, for the industrial consumer agent here, you can set the consumer preferences, and then you see how varying these parameters affects the bidding strategy. And the fact that it's time dependent means that you have time dependent decision making, as we've seen in the previous presentation. Different markets have different clearing times. So that's another advantage of simulation approach. And finally, the fact that you want to have the scenario exploration. So test different preferences, test different operational requirements, means that you can essentially quickly and easily replicate an industrial consumer agent to different types of agents with different properties and see how then they behave in a specific market. So this is then applied to a bunch of different industrial processes, ideally. So far, I've worked on the food cooling process here in the middle. And then the greenhouse is another application. So essentially here, the question is, you have a lower and upper temperature for the cooling, which you can vary your power within. For the greenhouse, it's more about shifting your lighting to decide that will influence the plant growth. For the wastewater aeration process, you essentially need to churn water to provide oxygen for the bacteria to digest nitrates and clean the water. So you can decide when you activate the pumps. For the cement milling, it's you decide when to crush a certain the kiln, so the rocks, to create the cement. And here, this electric arc furnace essentially melts down old scrap to produce new steel. And again, you can shift that specific process. And these all have very different properties. Some are purely thermal, some are electromagnetic, some are purely mechanical, some are batch processes, some are continuous processes. And so they all have very different flexibility properties. And the model needs to be able to adapt to these different types of processes. So that's on the process side. And on the market side, as I mentioned in the beginning, the Danish market has a certain structure, but the Chinese one will have a different one, which means through the agent-based model, you can then quickly change the information channels between some different agents. And that means they might have more market power or less market power because they have access to more or less information. The industrial consumer agent might actually know less or more about the prices, which will eventually influence its strategy. Of course, then the external price data will change depending on the market. The regulations or parameters you can adjust as well. So will it be half-hour clearing? Would it be hour resolution clearing? The functions of the market change as well, depending on the specific system you're considering. And then some sub-markets might not even exist. So this really underlines why you need this more modular, flexible approach, which in the end will all influence the participation strategy. And when I speak about strategy, this could be empirical strategies. I only want to bid above a certain clearing price, or I only want to bid at night, or I want, yeah, exactly. So this also depends on the consumer's behavioral preferences. So to give an overall wrap up of what this project aims to address is to give a standardized methodology for market participation evaluation. And the model framework developed in that context needs to be modular. So to adapt to different situation, it needs to be consumer centric, because in the end, it is the consumers who decide whether or not their energy consumption should be flexible. So it is focused on the benefits for the consumer and not for the system or for the grid. It is data driven. So all the market prices are fed in from historical data prices. And it is descriptive. So we're not giving an optimal path to follow. We're giving essentially an array of possible directions you can go in. And then it's up to the industrial consumer based on his own preferences to choose which way to go. And eventually, From all these different case studies, there should be some demand response strategies that are proposed essentially, or recommendations that can be made based on a specific process in a specific market context. So that's kind of the overall aim of this research project. I realized I didn't include actual results, but I guess that can be something you can tune in for tomorrow or the day after, because I'll be presenting some of that at the conference as well. So yeah, that's it.